So good afternoon everyone. For the lecture today, I'll continue the simulation of dynamical system and we're gonna use state feedback control. So last time we already simulate using ITC-DCLab. So we only simulate the dynamic system with an open loop where you have inputs as a step function into the dynamic system, and then you got the output as a car lateral motion H1 and H2. H1 is car lateral motion from here. So before I implement the state feedback control, let me review the theoretical part. Let me use duplicate, and this one's still working fine. Okay. All right. So the formulation of state feedback is U equal to minus K times H plus scaling coefficient KR times the reference. Okay. And you can write in the expanded form like this. And for the process to find K, you need to follow this. So once you substitute the control input U into the state equation, you can have this factor with the H. So what you need to do is to find the right value of K such that H converges as T tends to infinity. So the way that you can find value K is that you set the condition all the eigenvalue of this matrix are all negative. And how you can find eigenvalue of a matrix? Well, by definition, let me review a little bit. By definition of eigenvalue, you have let's call this matrix M. Oh, last time I call it a calligraph, right? Okay. So to find, by definition of eigenvalue, if you have a matrix A, then you time an eigenvector, let's call it V, then it just equal to eigenvalue times the eigenvector V. Okay. So then you can have A times V minus lambda times V equal to 0. Then you can have V as a factor. Then what you have inside here is A minus lambda I, okay, equal to 0. So for 0 eigenvector V, it's not interesting because of course we already know if you have 0, anything multiplied by 0 must be 0. But what is the most interesting is that if V is non-zero, what are the condition, or what is the condition for this whole matrix to be to have this equality satisfied? So the condition is that determinant of this matrix is 0. It's okay you use this one in front. I mean it's the same as lambda I, determinant lambda I minus A equal to 0, and you have A as A minus BK. So finally you can have determinant of lambda I minus A plus BK equal to 0. Then you substitute A, B and K, then you can easily find the polynomial equation of lambda, yeah, this equation, this expression equal to 0. Okay, maybe I put here. And from this, if we compare with the standard form lambda square plus 2 zeta omega n, lambda plus omega n square, then we can make the comparison. This term equal to this, and this term, this coefficient equal to this coefficient. Then we can easily find K1 and K2, right? K1 can be found first from here, and then K2 can be found from equating this term and this term. Okay? So now you already got the formulation for controller K1 and K2, and then you can find the KR following this formulation. And it's interesting that for this problem KR is actually just the same as K1. Okay, so now we can implement this for the simulation. First we need to define all the parameter. So we already have A, B and V0. Now we need to choose zeta and omega n, right? So let me find, let me open the parameter function. So not this one. Okay, I think I need to open a new one. Oops, what happened? Oh yeah, okay. So I'm gonna create a new function in order to define all the parameter. So actually for this one we already have A, B and V0, right? So we already have this, and then we choose zeta. Zeta, let's say equal to 1, and then omega n, let's say 2 pi times 3, and then K1 equal to, what is K1? Okay, so K1 equal to B times omega n square over V0 square, and then K2 equal to two times zeta times omega n times B over V0 minus A times B. Oh no, it's plus, right? Oh yeah, we don't consider the minus sign here. So minus A times B times omega n square over V0 square. Okay, and KR is just same as K1. KR equal to K1. Okay. I think it's 5. 5 or yeah 5, this one also 5. So psi 5, and then I say parameter for car kinematic. Okay. Okay, so now we can define all coefficient for all parameter for controller. Now let's build a feedback control here. So let me keep all the open loop here, and I will copy paste the new one, and I will modify the new one for control. Okay. Okay, just like this. Alright. So now the input should be obtained from the controller, right? We don't have step as an input to the system, but instead input u equal to minus k. I don't need to delete it. So what we have is input u equal to what? U equal to minus k times x and plus kr times rt. Here is u. So here is u. Here we can write as minus k times x plus kr times r. So I need sum. I need sum or add. Maybe sum is fine. This one. So but this one there's too many input port, right? Okay. Let me try to configure it. Cannot configure it. So anyway, let's try to use it. Then we have h time. So we need gain. Where can I get gain? So in here I don't have any gain. So I go to here, I get gain. So in this gain we can so in ITC-DCLab, in ITC-DCLab we need gain K1. So here K1. Okay. Incorrect. Look, let me see here. Do I have K1 already? Not yet. Oh, it does not recognize pi. So it should be 3.14 and 16. Run again. So now I get K1, K2. Now it can recognize K1 and K2. So here I think I can put K1 and K2. Yeah. So K1 times X1. So I need X1 here. Okay, let me copy to have H2 or K2. K2. So where can I got the H1? Oops. Okay, this is H1. How about H2? Let me change this one to K2. Okay, and then we need this one should be minus, right? So maybe I should change to be minus. Yeah, I need to change to be minus K1 instead, and this one also minus K2. Okay, so this connect to this, and this one connect to this one, and then this is a reference R times KR. So here should be need to be KR. Okay, so actually here is a complete state feedback already, and then I can run. Well, I need to run the function car lateral motion. Yeah, this one. This function is already defined, but we need to run it first. Okay, run it. Already execute, and then we run this model. But before I run it, I close all the graphic first. So run. Refreshing period takes so much time. It takes so much time, so I think I stop it, and let me reconfigure the parameter. So this one refresh period is 10 seconds. 10 seconds may be too long. Let's observe at 2 seconds. First, just 2 seconds. And how about this one? Oh, look, 2 seconds. No, it's too short, right? It's too short. I guess, yes, maybe 10 seconds is already good. Yeah. 10 seconds is already good. How about this time? 0.001. This one also 0.001. It seems good. How about simulation time here? 20 seconds. Let me change to just 10 seconds as well. And let me run again. I should close the graphic first. and run it again. Y-axis, this one is y-axis is too big, right? I need to change y-axis too. So y-axis, yeah, last time we tried very large y-axis. Now let's see, y minimum is from 0 0, maximum like up to 5 meter. This one also maybe just 5, and this one is just from 0 0. Okay, and let me try again. Yeah, so actually because the reference is 1, it's like, okay, move to the left 1 meter, right? So maybe just plot from 0 to 1.5 for this one, maximum just 1.5. Let me try again. Yeah, it takes so long to compute this. Actually we can just see around 2 seconds, right? So very quick, right? Yeah, because the car is running very fast at 25 meters per second. Actually it's very fast. To see more graph, then I will change the simulation time to just 5 seconds, and y-axis takes from 0 to, for this one, just 0 to 0.5. This one it's fine to be 1. Yeah, try again. Yeah, ten second because this one up to 10 seconds, right? So let's use 5 seconds. This one also. Okay. So look at this result. How can we interpret this result? So actually H2 is related to the steering angle. If we look at the equation, H2 dot equal to U times a constant, right? So H2 is just integrate of steering angle. Okay, integration of steering angle, because H2 equal to some constant times U. Okay, so in order to move the car to the lateral motion, or for example to the left, the integral of the value of steering. So if the value of H2 approach to 0, it means you move the steering angle to the positive, and then you move to the negative, such that the area under the curve of the plus and the minus are equal. Okay. Okay, here you can see H2 equal to V0 over B times U, which means H2 is integral from 0 to T V0 over BU d tau, which means if you have U like this, if you have U like this, H2 is the area under the curve, so this area is plus, and this one is U. Okay, this area is minus. Then if you integrate U, it means you add up all the area. So when the area is 0, it means your H2 is something like this. First it go to the positive part, and then it come back until 0 like this. Because if you want the car to move to the left, but then it keep the direction straight along the road, you need to steer to the positive, and then you need to steer back to the negative before you have the steering at 0 angle, right? Okay, this is how you interpret the result of the simulation here. And it's also interesting to look at the control input that I just mentioned here, U, right? Yep. So let's modify our modeling to see the graph of control input U. How can I do that? Can I configure this one to be 3 port? Let me give another port like this. Alright, so I need this one 3 value, and this one also 3, up to 1.5. I'm not sure it's possible or not. Let's see. Yeah, okay, it is possible. So let me expand this one a little bit. So the control input here will be recorded to see the value. Okay, so let me run again. Oh, for the graph number 3, not 0 to minus to 1, but yeah, it also has a negative value. So the minimum should be, let's say, from -5. Maximum is 5 for the control input. Okay, yeah, that's too big. So -1, -2, maybe -1 to -2, or to 2. Okay, let me change here from -1 to 2. Yep. Okay, now it's clear, right? First you steer to the positive, and then you come back, steer to the negative before you keep it straight as a 0 angle. So it's very quick, right? Just less than a second. Why it's less than a second, right? Because we choose omega n too big. If we choose omega n slow, maybe you move it a little bit slow and then you come back slow, right? So how? Okay, let me try again. Let me choose omega n smaller. Not that one, this one. Let's say I reduce this one to just 1. Okay, then run it and then run this one again. Yeah, so now you move a little bit and then you come back very slowly. Okay. If I want to see this one clearly, maybe I can reduce the min max value. Okay. Min to be minus 0.3, max to be just 0.5, and then try again. This is the old one. Yeah. Okay. So now try yourself. Oops. Okay, try it. Okay. Do you have any question? This one? This one is just the same as this one. This one and this one.